All right, welcome back. We're going to dive right into the next lesson for our physics unit, and this is lesson 1.4, electric circuits. So before we get going in circuits too far, we want to make sure that we know the different parts to circuits. So you've probably done circuits at some point in your science career up until now, but let's make sure we're all on the same page. So 4 main parts of the circuit. We need to have conductive wires that move the electrons, and they're made up of a conductive material like copper. There's an energy source like a battery. All right, so typically our battery is our energy source. There'll be switches that you can use to open or close the circuit. Right now, this switch is closed because the electrons can flow through that wire. If it was drawn open like this, then the switch is open and the circuit is not happening. It's an open circuit. And then we have load resistors. This is a device that turns the electrical energy into another form of energy. And there's an example of a light bulb taking the electrical energy and turning it into light. A couple other things about the parts for safety. You've probably seen this before. The plastic material around the wires, that's for insulating, and so that we prevent heat from kind of causing any damage. Like, so in your house, you wouldn't have bare wires. You would have these wires covered with the plastic. It also helps prevent short circuits. So if the wires happen to touch each other, they're not going to conduct the current through to the next wire because the plastic coating prevents that. All right, so types of circuits. You may or may not have done this before, but should be a little bit familiar to you. We have something called a series circuit, and we have parallel circuits. So a series circuit is when there is just one possible pathway or one loop for the current to flow. An example of this is when you have those old Christmas lights. You've probably seen the Chevy Chase Christmas Vacation movie, maybe, but he spends hours and hours, him and his son, hours and hours testing each light bulb because one light bulb is out in the strand, and if one light bulb goes out, the whole strand goes out. So this is an example of a series circuit here. Here's your battery. If you follow the electrons, they can follow one path through all of these lights, all these loads, through the switch because it's closed, perfect, and back to the other end of the battery. So there is one continuous pathway, one loop that all electrons will travel. All right, so that is what's called a series circuit. So when one burns out, they all go out. And contradicting, like the opposite of that, is a parallel circuit. So in this kind of a circuit, there are multiple loops, loops within a loop, multiple pathways for current to flow. Okay, that's the key. So example of a parallel circuit, this is going to be what you're going to have in your home, in your house. Like if one thing goes wrong in your house, all the things don't go out, right? So when you have a power bar, so the idea is a parallel circuit. When one burns out, the others still work. So this is what we need in our house. We don't want one light bulb to burn out and the entire house circuits are useless. That would not be good. All right, so our pathways, you can visualize them. We're going to start at the negative end of the battery, and we're going to find a pathway. Oh, here's a pathway through the one light bulb. Turn that light bulb on and go back to the battery. Alternatively, you could have an electron current going through the second light bulb and back to the battery. Or you could have current going through the third light bulb and back to the battery. So there are actually 3 paths in this parallel circuit that the current or electrons can take. As opposed to this one, there's only one path. So one path for series, and parallel can have multiple, at least more than one. All right, so these are some of the symbols you're going to be working with in this section. You do need to know most of these, or all of them, yes. Okay, so first, actually the next page has all the, what they all are. So why don't you pause the video right now, see how many you know by the descriptions, and then you can see if you get it right. So pause the video. Alrighty, so hopefully you paused, took a second to just see how many of these you already recognize. You've got the wire, which we already went over, so it's just the straight lines, and where wires join, you'll see another wire. You've got an open switch in this case, a closed switch, this line would be connected to the next one. When you see a big line and a small line parallel to each other, that is your power source or a battery, and a lot of times it'll give you the voltage of that battery, but sometimes it might not. Here is another way of looking at a battery. So this is can be multiple batteries together. So this would be 1 battery, 2, 3, 4 batteries in that case. And sometimes you may or may not be given the voltage of that battery. This is a resistor. This is something that slows down or resists the flow of electric current. And that's a symbol for the lamp that we've been using. It's like a little loop and then a circle around it. It's like a little light bulb. Here we have a voltmeter, so this measures voltage. We have an ammeter, which measures electric current, or amps, which you're going to learn about. And you have an ohm meter, which measures resistance, which again, you'll learn about a little later. We also have these fuses, which are safety devices that are put into circuits. So if the current gets over an acceptable level or a safe level, it'll actually shut the current off. It'll blow, and then you'll have a space in your current that no electrons can go over. All right, so what is current? Current's the amount of charge. The amount of charge, otherwise known as electrons, the amount of electrons that pass a point in every second. So this visual here helps you think of that one. So you got electrons moving, and you're going to time it for 1 second. How many electrons pass this point in 1 second? And that will be your current. Electrons are moving from the negative end of the battery to the positive end, but they might have to take a path, right? So they're going to start at the negative end of the battery and go through to the positive end. This is not the same as an electric field. Just remember that. Okay, electric fields, you're using a test object of a positive, and you're going to see which way it goes. It's going to the negative. Anyways, so it's kind of opposite the direction. So keep that in mind. Current, though, current is represented by an I, a capital I. So if you see it in an equation, a capital I stands or represents current. But the units of current are amperes, or capital A, amps. All right, and we use an ammeter. Well, this is good. An ammeter to measure current. And when we put an ammeter into our circuit, it has to be in series. Okay, it has to be in series. I'll show you what that means in a second here. Oh, here we go. We've got it. Actually, there's 2 diagrams. Here we go. We have a battery going to a load, which is our light bulb, through, this is our ammeter in this case. Ammeter. And then back to the battery. So all the electrons in the circuit have to go through the ammeter to be able to measure the current. Okay, so that's why we say current or ammeters are measured in series, because they have to be within that series pathway. So all the electrons will go through it. Alrighty. Now, another term that you're going to come across when we're dealing with circuits is voltage. So, batteries, we've talked about what they're represented by. So that's a single battery. There's 2 batteries hooked together. These 2 batteries here are in series. They're back to back, so they're in series. So batteries can create voltage, which is basically the amount of electrical potential energy. So how much the amount of energy that's available for doing work. Okay, so it's the amount of energy you have that's available to do some work, to make that current go. So voltage is what causes the movement of electrons and creates the current. And we measure voltage in volts. All right, and voltage is also represented by a capital V in equations. Go figure why amperes is measured, current is measured by an I, but the units are amperes. I don't know, but you do need to know that. I should look that one up. All right, so now if you're going to use a voltmeter to measure your volts, like you use an ammeter to measure your amps, you need to connect it in parallel in the circuit to measure the voltage. So it doesn't go in series, it goes in parallel. So if you're trying to measure the voltage of this series, this is a series path here. You've got a battery going to a light, going back to the battery. To measure the voltage, you don't put it right in the middle of the circuit like you do with the ammeter. You go on either side. You see the clips are going on either side of your load, and that's where you're going to measure your voltage. Okay, so that in a diagram like this, you can kind of see the difference on how they're laid out. So here's your battery, your wires, here's a resistor here. I don't know why they don't have a resistor, but whatever. And here's another load thing. Basically, if you want to measure the voltage, you have to go on either side to measure the voltage. Okay, so now see how we've created another path, so the electrons could either go right through or they could go through the voltmeter. So this is now in parallel. We've added the voltmeter in parallel. The ammeter, however, all the electrons in that current have to go through that ammeter, right? There's no other way around to get to the other end of that battery. Otherwise, you have to go through the ammeter. So that's in series. So the ammeter is in series, a voltmeter is in parallel when you're measuring. So just here's a little analogy that might help you remember what these terms are all about. So voltage can be represented by the pressure in a water tank forcing the water through the pipe. Okay, so there's your downward pressure. That would be your voltage. And then your current would be the water flowing through the pipe. That represents the electrical current. The more pressure there is, the more current you're going to get, right? The higher this tank is, the more pressure you're going to get. So you're going to get more current. And then a resistor could be the small diameter of this pipe. It's going to restrict the water flow the same way a resistor would do. So it's going to kind of slow down. You can't get as much current through there. So when you are in a lab, you would be using a multimeter. So this is a multimeter here. And this multimeter can measure a lot of different things. It can measure voltage, it can measure amps, and it can measure resistance in ohms. So you need to make sure, first off, you're setting it up correctly when you're measuring and knowing what you're measuring. So in this case, this dial, this white end of the dial, that's what it's pointing to. And over here, you can see this whole section here is amps. So if you've got it pointed here, 200 milliamps, that means you're measuring in milliamps, which is current. Right? So amps are current. So if you're measuring in current, you need to make sure all the electrons from the power source in that circuit are going through it's now considered an ammeter, even though it's a multimeter. But if you're measuring amps, you're measuring current. So you need to have a series pathway. And you do. All those electrons are going through the whole pathway. Okay. Now this is different than here now we're measuring and we're looking at volts. So right now we're measuring volts. So this is 4.34 volts on our voltmeter. The difference is here's our power supply or battery, whatever you want to call it. In this case, it's power supply. Here's a resistor our electrons can go through and go back to the power supply. But we want to measure the voltage. So we come in on either side of the object or the item that we're wanting to measure the voltage for. And you see, we've created another whole pathway. So this is in parallel. So we've added our voltmeter in parallel to measure the voltage. All right, here's a little practice question. It might be something that you're going to see along these lines. So which circuit diagram below correctly shows the connection of an ammeter and a voltmeter? Remember, all the electrons have to go through an ammeter, and voltmeters create their own pathway. I'm not sure if the answer is on this page. Oh, no, it's on this page. Okay. All right. So, oh yeah, the answer is right down below there. So number 4, you can see here's our battery. All the electrons are going to go through that ammeter. It's the only way to get back to the other end of the battery. However, they could go through the resistor or they could go through the voltmeter. So the voltmeter is set up in parallel and the ammeter is set up in series. In this one, the ammeter and the voltmeter are both in the same one single path, so they're both in series. Let's take another look at another diagram. In the circuit diagram below, label which 1, 2, 3, and 4 are ammeters and which are voltmeters. Alrighty, so here we have our battery. And we're going to go through here. So all the electrons are going through number 1. So this is going to be an ammeter because it's in series. And we're going to go through this resistor with our ammeter. So we can use this ammeter here. This ammeter is in series. And if we follow the pathway through this next resistor, we are not going through this device, so this must be a voltmeter. These two are ammeters. That must be measuring voltage. And then the same thing with this. It's created a whole new path on either side of the battery, so this must be measuring voltage. So if you want to get, okay, so this question, in the circuit above, where should you put your ammeter if you want to correctly get the total current? Well, there are 2 paths in this, right? So I'm going to draw the other pathway in a light blue. So you can see here's one pathway that electrons can take in this circuit. And then the second pathway is through the next resistor. So we actually have a parallel circuit. So if we want to check and make sure we're measuring the current for the total circuit, we need to make sure all the electrons are going through that ammeter. So number 1 is the only place where all the electrons are going through the wire. This ammeter here too is only going to measure the current for the blue, right? This blue circuit. Whereas 1 is going to measure the current for the pink and the blue. Okay. All right, so when we put batteries in series is a way that we can increase the voltage of a circuit. So every time we add a new battery in series, we increase our voltage of our circuit. So you can see the formula here for total voltage. If you are having 4 batteries, let's say there's a 4th here. So the total voltage, you're just going to add up the voltage for battery 1, the voltage for battery 2, battery 3, and battery 4. So here's the example here, and we're just literally adding up 1.5, 1.5, 1.5 volts, and we get our 6 volts. So our total voltage, when batteries are in series, you just add up all the voltages. Okay. Now, if batteries are in parallel, they do not add up. So all of these batteries here will not add up for the voltage. They're just going to equal the total voltage. So the trick with this, it doesn't actually increase the energy output, but what it does if they're in parallel is it can last longer. So you can make these batteries last longer if they're in parallel. Okay, so just a little reminder, visual here. So in this case, the batteries are in parallel. So the light's going to be dimmer, but it'll last longer. Whereas over here, you put the batteries in series, the light's brighter, but it's going to get drained faster. So it's going to be a shorter amount of time. All right, so in this case, this is an example, find the voltage supplied to a stereo operating with 4 1.5 volt batteries in series. So if the batteries are in series, remember that's going to mean that they're going to add all up. So the total voltage is going to be equal to the voltage of the first thing, the second battery, plus the voltage of the third battery, plus the voltage of the fourth battery. So you're going to add up all your batteries voltage and you get your total voltage. Now we're going to take a look at resistors. So a resistor is any device in a circuit that can disrupt the electron flow. So they might disrupt it to generate heat for a heater, or to like make it go through a wire so that we can create light. So some examples of some resistors are light bulbs, a toaster. You're going to make it go through wires that can heat up. Light, stereo, any kind of wire even can be considered a resistor. So resistance is measured in ohms, and there is the symbol for ohms. And when you have resistance in a formula, it is capital R. Okay, and we measure resistance with an ohm meter. And the symbol for a resistor or resistance is this squiggly line. It's a fun one to draw. All right, so we're going to do some circuit drawing practice now. So we're going to draw a circuit with two cells, aka batteries, in series, and two resistors in parallel, a voltmeter, two voltmeters, 3 ammeters, and a switch that turns off the entire circuit. So if I have two batteries, you might want to pause this and see if you can draw this on your own first. We have two batteries in series. So we have two batteries in series. There's our two batteries back to back. I'm going to start with that. Done. All right, so those are done. Two resistors in parallel. Well, it's easier for me to visualize if I draw my resistors beside each other, parallel. So let's just do that. We have two resistors in parallel. Done. So we have a voltmeter. And we have 3 ammeters and a switch that turns everything off. All right, so where are we going to put our switch? I'm going to put our switch before we get to all our different resistors or loads or anything. So I'm going to put the switch here so that when I close it, no electrons could get to any of these resistors. And then I'm going to complete my circuit. So if this switch closes, I can have electrons going through the first resistor and back to the battery. I can have electrons going through the second resistor going back to the battery. So I have a parallel circuit here. Now I want to put 2 voltmeters in. I'm going to have to put my voltmeters in on either side of whatever I want to measure, but I need to make sure I create a new circuit. So I'm going to put my voltage, I'm going to check the voltage of this part of the circuit here. Voltmeter is just a V with a circle around it. And I can throw a voltmeter around the other resistor if I want, but I'm just going to put it over on the other battery here, on either side of the battery. Remember, voltmeters have to go in parallel, so they create their own little loop. However, ammeters, if I want to measure the current, I'm going to put 1 ammeter here so I can measure the entire current of this circuit, because all the electrons have to go through that ammeter. I'm going to put an ammeter here in series, but it's only going to measure the current of the electrons going through this second loop. And I could put an ammeter in here to measure the current of the electrons going through this first loop when the switch closes. All right. Calculating resistance. So these formulas we're about to look at are on page 3 of your data booklet. So take a look at them. Find that. You need to know where to find all these different formulas. So when resistors are in series, so right, they're all in a line here, right? One pathway between all those resistors. Then you total up all the resistor values. You add them all up to get your total resistance. If those resistors are in parallel, you have a different kind of formula here. And this is where we're going to practice this formula. So here's an example of resistors in parallel, right? We just drew one of those examples. All right, so let's do some practice so you can see how these two formulas work, because this one is quite unique. All right, so example 1, calculate the total resistance of the following circuits. So we have a resistor here, and resistor here. This is a series circuit, There is only one pathway through all those resistors. So our equation, make sure you look on page 3 to see in your data booklet where this equation is. It shows that you're just going to add all these different resistors up. So we have 4 ohms plus the resistance of the second resistor is 3 ohms plus the resistance of the third resistor is 2 ohms. Add them all up. 4, 3, 7, 8, 9, 9 ohms is our total resistance. Pretty straightforward. So if they're in series, add them together. If they're parallel, like this case, then we have a slightly different way of dealing with this. So watch this carefully. So we're going to have 1 over our total resistance. So remember, that's 1 over our total resistance is equal to 1 over our first resistor, our first resistance, which is 4 ohms, plus 1 over 3 ohms, plus 1 over 2 ohms. Now, if you're in math class, you'd be like, ooh, I see, I'm going to add fractions. I need to get common denominator, yada, yada, yada. Okay, you can do that, but sometimes it's not that easy. So I'm going to show you the shortcut. You can, not shortcut, but probably the method that is easiest and for this kind of a question. Just get rid of the fractions. So we're going to go 1 divided by 4, which gives us 0.25. We're moving to decimals here. 1 divided by 3 gives us 0.33. Don't have to write them all. And then 1 divided by 2 is 0.5. Let's add all these up. And we get 1.083. But this is not our total resistance. Not yet. This is equal to 1 over our total resistance. Okay, really important part here. So there is a final step to get just RT alone. We need to flip this. So we have to go 1 over 1.083. So let's do that. 1 divided by 1.083. And that is 0.9236. And let's look at our significant digits. Well, we only have one significant digits in all of our ohms. So this has to equal 0.09 ohms. There's your answer. So you can see when you have resistors in parallel, same resistors, your resistance goes way down. It's lower than all of them, each of them, right? Lower than our lowest one. Alrighty, so there's a couple more example questions for you to do. If you don't understand what's going on, make sure you do these. This is one where you have to find the total resistance in a series circuit containing these 3 different resistors. So you just add them all together. Oh, this one got all jumbled up. Hopefully your slides are a little bit better than this one. This is a string of 8 lights connected in series again that has a total resistance of 120 ohms. So you know that all 8 of your lights have to add up because you're in series. They all have to add up to 120 ohms. So you're basically just doing 120 ohms divided by 8 lights to see how much each resistance, the resistance of each bulb is. Alrighty, I'm going to leave you with this practice question here. There's a lot of information and the answer is given, so make sure you practice this little practice ditty. And here's a nice review of series and parallel circuits and the current, voltage, total resistance, and then what happens when one resistor fails. So make sure you go through that when you're going and reviewing these slides. Actually, maybe I'll just quickly go over this one here. So there's a general diagram for a series. You're going right through everything in your circuit in just one path, whereas a parallel will have multiple paths. The current through each resistor, if you're in series and it's going to be the same current through every resistor. And then if it's parallel, it's just going to depend on the resistor, how much current is going to go through there. We haven't done all this quite yet, but if you're talking about voltage, all the voltage is going to depend on the different resistors. Okay, yeah, that's something that's coming up. Our formula to create total resistance. So if you're going to calculate total resistance, there's your formula. You just add up all your resistors, but in parallel, you're adding up 1 over the total for all your resistors. So very different formula. Your total resistance throughout the circuit, if it's in series, it's going to be a high number. It's going to be higher than all the 1 resistors combined, and then this resistance is going to be much, much lower than in series. And if 1 resistor dies, they all go out. If the 1 resistor dies in a parallel, just that 1 loop will go out, but the rest will still work. All right, I'm going to pause there. That was long enough. If you have any questions, make sure you get a hold of me.